when you have the birth of a star, you basically have the birth of the whole system, the planetary system. So our whole solar system came about from the birth of the sun. So the sun is like 98, 99% of the entire solar system as far as mass and what it makes up. So all the rest, all the debris is like the planets and everything else we'll talk about in chapter 6, 7, which I'm combining together because we're just gonna say all the bodies of the solar system in chapter 6 and 7. We'll combine those. And then we'll look at the birth of all that stuff in chapter 8. So without the sun, we wouldn't have the solar system. We're finding a lot of other systems out there very similar and understanding the process of planetary system birth. So our sun, we know, is about 93 million miles away. That's what typically is stated if you ever watch documentaries. And it's about 4.5 billion years old. So the solar system is about a little older because before the sun became a star, it was what we call a protostar. There was a little bit of time before it actually formed. And it's estimated to be about 5 billion years left. Now, be aware that I ran across that National Geographic video I posted. It's really good, except for they had a different estimate. They said something like 6 or 7 billion years left. The most accepted is 5 billion years, but nobody really knows. It's really dependent upon how long we have the fuel inside the sun to make the light that we see from the sun. Okay, so the sun size is huge. Okay, so at the equator, so there's different sizes. It's a ball that's not equidistant from the center everywhere. So you have to think it bulges more at the equator than it does at the polar regions. So at the equator, we're having about 100 Earth diameters. Okay, so we could put 100 Earths across the sun's equator. That gives you a scope. The mass is huge. Okay, so you could fit over 1 million Earths inside the sun. Okay, and the main composition, hopefully you got these numbers too, is hydrogen. Okay, we're looking at almost 74% hydrogen, and these numbers will vary depending upon what references. These are the most updated ones I found. Okay, so be aware, they're usually roughly in the same range. And it's not exact because, we haven't had instruments that we could get that close and actually determine. So we have a lot of models that predict these ratios. So about 74% hydrogen, 24% helium, and that about 2% or less is the heavier elements like oxygen, carbon, nitrogen. So that's what we mean by the heavier elements. Surface temperature, to be exact, 5,778 Kelvin. And again, we use spectroscopy and a lot of our temperature models to figure that out. We have a lot of observatories studying the sun. Okay, and one of the fascinating things we'll see is that above the surface of the sun, it's actually hotter. So this is really in the corona. Interesting science that's still trying to be, there's a lot of research in that science still. So for ease, to try to convert on scales, Kelvin is what we use again in science, and 273 Kelvin is equivalent to 0 degrees Celsius, which is the freezing point of water, which is equal to 32 degrees Fahrenheit, the freezing point of water. So that gives you a scale. There's a lot of great converters online that will do all Fahrenheit to Celsius to Kelvin. Okay, and 273 Kelvin. The lowest temperature we have in science is 0 Kelvin, and we say that's absolute zero. So we've we've worked our way through that scale. The luminosity is measured in watts. It tells you how bright the sun is. So how much photons are leaving the surface over a given time. So that's the power it gives off. The luminosity, the power, and the brightness. The color appears yellow due to the atmosphere, but emits greener light due to temperature. Now, the rotation is really interesting in the sun. different parts rotate at different speed, and we'll see that's called differential rotation. So at the equator, it rotates once every 24 days, while at the poles, it's once every 35 days. And a good question is, how do we know that? Well, we'll look at sunspot activity. It's a G25 main sequence star. So we'll learn more about the classification of stars. So this is the sun's classification, the sun R stars classification. And G is by temperature. 2 is the degree of temperature. We have different levels of temperature. And this 5, this is a Roman numeral 5 right here. And that tells you what kind of, we're on this star diagram called the Hertz-Russell diagram. It exists, which really means it's a main sequence star. So we'll explore that more a little later. So let's go through. I'm just going to pull something up real quick here. I'm going to use my ink pad. Okay, so some facts. So we say the sun is a hot ball of plasma. So it's just excited gas, okay? And when you heat gas up, you have these charges. Charges meaning protons are positively charged particles, electrons negatively charged particles, and other particles too, but those are the ones that are within atoms. So you have these charged particles that are just swirling around there. So it's generating electricity magnetism, so to speak, so inside there. So it's really, really, you know, via the temperature of the sun is so much that it's creating these conditions that make it excited. So going back here, we have an expected lifetime of 5 billion years to go. So we'll talk more about that in future chapters. But as I stated, the birth of the sun is key to the solar system we know today. Okay. The main way the sun produces its light energy, and we'll talk about this and other stars, what distinguishes the sun, our star, from the other bodies of our solar system, like planets and moons and all the rest, is the fact that the sun makes its light through a process called nuclear fusion. And I have a slide coming up about nuclear fusion. I don't expect you to know all the details, but the idea behind fusion is what we have is the sun is so massive. And as we noted from chapter 3, the more mass you have, the more gravity you have acting on it. So there's a lot of gravity squeezing the sun, the gas of the sun together. And as it squeezes the gases together, the atoms are like getting close together, are getting fused together. They're getting smashed together. So we have an atom of hydrogen, another atom of hydrogen, and they're squeezed, they're pushed towards one another so that they fuse, combine, and they produce a helium atom in the process. And the helium atom is a little lower mass, so by conservation, mass, and energy, there has to be a little left over of something, mass or energy. So that's the energy left over. So by fusing a hydrogen and hydrogen, you produce a helium atom and energy. And that is a process for all the stars we know of. There's some strange stars out there that don't quite fuse, but what we say is what made our sun go from its proto-star stage to the star stage is the fact that it underwent fusion. So that's how it makes its light. Huge process. So fusion is different than fission, which is the splitting of atoms. Okay, so the sun was much cooler in the past too. It's went through a lot of phases and it's still evolving. So some things to know. And when we run out of hydrogen fused, then it'll begin its next phase of stellar evolution, something we'll visit back to. So some of the key ideas, and what I have you do on the worksheet is, we use our sun's facts as references in comparisons to other stars. So a lot of times we'll say, well, this star is five stellar masses. That means we'll know this the rough mass of the sun, and we'll say this star is 5 times more massive. Or we'll say, we'll base it on the luminosity. If we know how bright the sun is, we might say, here's a star that's like half that luminosity, and we'll understand how much less bright that other star is. So we use it for a lot of comparisons to other stars. So that's why I had you go through some of the facts and listing all that information. Okay, so here we go. So here you can see there's different parts of the layers. We have layers of the sun, okay? And we're going to see that we have the core here. And this is where the fusion undergoes. This is where it's so much pressure, right? Everything's squeezed in, that this is where the sun is making its light. Okay, so before I go through all these layers, 2 terms to be familiar with that hopefully are not baffling you when you're reading this literature in the chapters is radiation. What happens is in this radiative zone that we'll see, lost my, oh, need a, okay. We'll see in this radiative zone that the light made here gets absorbed by the atoms in here, re-emitted. Atom takes in a frequency of light, then spits it out, takes it in, spits it out, takes it in, spits it out. That's what we mean by radiative processes, radiation transfer. So what we have is the electromagnetic waves, or the photons, are being emitted atom by atom in this zone right here. And that's how we transfer the energy. So we know the sun makes a lot of energy. Of course, we could feel that, right? On an everyday basis. Convection is a little different. It's the moving of fluids, like the hot gases rise, and then the hot gases rise. Whoa, let me get rid of that here. I'm still playing around with new tools here. So the convective zone, we have this cycle. It's like a lava lamp, right? So what happens, hot gases rise and then it cools and sinks. Gases rise, cools and sinks. So the convection zone is what happens right there in the sun. So that's another layer. And then we're gonna get to the photosphere, which is the surface of the sphere, and the chromosphere, which is the atmosphere. And then where you have the corona. We'll talk about what the corona is. So important layers of the sun. And there's some good websites links that I've posted on our page that are good to visit, that have really good details on this. The sun is still a very mysterious object, so that we're doing a lot of research on. So let me see if I can move. Okay. I'm going to try to see if I can move this. There we go. So you could see here you have the core, and this is about 20–25% of the interior, the inner core. And then the radiative zone goes from, this is not really accurate, 70 to 75% up. I think I'm going to have to adjust this figure right here. This goes to 25 to 70%. My bad. Okay, good. So let's see. And then we have the radiative zone right here. Okay. And then we have the convection zone here, and then the photosphere, chromosphere, and corona. So there's really 6 layers that you want to know. Inner, radiative, convective. You don't really have to know about the subsurface flows, but then the photosphere, the chromosphere, and the corona. And each one of these I sort of detail. Now the core, this is what's really fascinating. We're talking about something that's 15 to 60 million Kelvin. That is hot, okay? And what you want to think of is, here's the interior. This is where the fusion's going on. The hydrogen is being turned into helium. And it could take, you know, thousands of years to a million years for a piece of light made right here in the core to come all the way to the surface. And then when it comes to the surface, if you remember back from chapter 1, it only takes about 8 minutes to get to Earth. So, you know, it takes a long time for those wavelengths of light or photons of light to get to the surface, because they're being absorbed or emitted, mixed around, etc. Okay, so the radiative zone is where we're doing, this is high plasma density. This is where we think the magnetic field activity is produced in the sun, and we'll see this is something we're very interested in, is the magnetic field activity of the sun, because it has effects to us here on Earth and a lot of our orbiting satellites. Okay, so the magnetic field, magnets we know have 2 poles, a north and south pole, and north and south poles attract one another. Same polarities don't, they repel one another. So the way you make magnetism is by moving charges around. So if you have free electrons or ions, charged particles, if they're swirling around, that's how you actually make a magnet. So anytime you see a magnet, inside there is jiggling electrons making that magnetic field. So that is what's happening right here, is you have magnetism starting out right here. Okay, and the temperatures are still hot, but nothing compared to the core. So let's move on to the next slide. Then next we have the convection zone. So this is the last 70 to 100%, and the energy is transferred via convection, which we talked about. So a few million Kelvin to approximately 6,000 Kelvin to the surface. So this is the last interior shell up to the surface. Now, when we talk about the surface of the sun, we're talking about the photosphere, and that's the visible surface we see. That's where we see the light and use a spectroscope to actually see the wavelengths come off of it. And this is how we discovered helium. Somebody took a spectrograph, looked at the surface, and said, "Wow, I see interesting lines there. There's an element there that we've never seen before." And once we discovered it in the sun, then we're able to look for it on Earth. Okay. Now the chromosphere refers to the atmosphere, the inner atmosphere of the sun. And you would think this is very bizarre. The interesting thing is when you go from that inner, that surface and above, it actually gets hotter. And that is because you have trapped gases. You have a lot of activity from the sun that's connected to its magnetic field activity. And we'll see that it's twisting and turning some of its magnetic field, and it actually traps gases in the atmosphere, creating these hotter temperatures. And then when you get to the corona, the hot aura of plasma above the surface, these are just loops of trapped gases, plasma, and the temperatures range from 1 to 20 million Kelvin. They're so hot, they give off X-ray emissions. And the big idea is that the energy is carried through the magnetic field, and it deposits heat, and then it makes the overlying plasma really, really hot. So there are so many different probes out there, like the Parker Solar Probe that was launched in 2018 is really looking at the corona, studying it more in details, because this whole process of trapping heat above the surface of the sun is new science, and there's a lot of research there. There's a lot of other observatories beside that studying the sun and the corona in particular. So really interesting area. So this kind of goes through what I was talking about, how it makes its light in the core. Okay, so we have 2 hydrogen atoms pushed together to make helium plus energy. A lot of times, instead of saying nuclear fusion, they'll say thermonuclear fusion. Okay. And getting back to the color of the sun, Okay, and what we have here, the color of the sun is based on this approximate temperature. It'll produce most of its light in the green wavelengths. And the yellow color we see arises from the interaction of the sunlight with our atmosphere. So as the sunlight, if you're looking at it from the moon, it'll look whitish. And it has to do with coming off the surface and interacting where it's at. But then as it travels through space, it goes through, you know, it goes through different phases. So depending upon what's absorbing the sunlight and re-emitting the sunlight, it will give you different colors. So in our own atmosphere, it'll appear yellowish when it finally gets to us. Now, here's a problem. I posted this example online. There's an example problem, and you could try this for yourself. Here's Wien's law. So if you want to figure out what peak wavelengths a star, or in this case our sun, gives off, what you do is you use this law right here based on the temperature. If you know the temperature of the object, you could put that temperature. So I put 5,800 Kelvin right in here, and I would figure out what the peak wavelength is. So if we do this right now, what would you get? So take this number, 2.9 times 10 to the minus 3, and divide it by 5,800. And this, there's reference cards to Wien's law in your textbook, but this is the most basic radiation, black body radiation equation used to link temperature and wavelength. Okay, I get about 500 nanometers. Okay, and that's in the greenish part of the spectrum. I get 5 times 10 to the minus 7. If you wanted to do that number first, you'd say 5. And I'm going to say 5 times. Excuse me for a second. This is a little slow. 5 times 10 to the minus 7 is what you should get, maybe in your calculator. Which is, whoa, not all that. Which is equal to 500 nanometers, greenish light. Okay, so remember 400 nanometers is on the blue part of the spectrum, 700 nanometers is in the red part of the spectrum. So that's what you should get in applying Wien's law. And you could do the opposite as well, and which is what I have. So if you know the wavelength, let's say you're studying a star and you're seeing really red light like 700 nanometers, you would put 700 times, or 7 times 10 to the minus 7 here, and you could figure out the temperature of the star. The T stands for temperature. Okay. So really useful equation there. And let's go ahead and go back here. So the sun rotates, spins faster, as we talked about, at the equator. Here's the sun's equator, then at the poles. And we'll see sunspots traveling this way. When sunspots, which we'll talk about, appear, they start at the polar regions and they make their way down and they spread out. So you have to remember the sun is just a ball of gas. It's not a solid body. And this idea of differential rotation we'll see applies to our gas planets, like Jupiter does this as well. Okay, spins at different rates. And then Saturn as well. So when you have balls of gas like that, you'll get this swirling pattern of gas and all these different velocities. Now, what's so important about this differential rotation is it is what's responsible for making the magnetic field the way it is. And the change in polarity. We'll see that the sun has a north pole and a south pole, just like the Earth. We have the north geographic pole and the south geographic pole. But what happens is these flip, okay, much quicker than the Earth because of how it swirls so quickly. All the hot ionized gas swirls around. So we'll see that every 11 years, this North Pole becomes the South Pole, and this South Pole becomes the North Pole. In the process, it wreaks havoc on the surface of the sun. Okay, and we'll see sunspots appear, we'll see flares, and we'll see all kinds of dynamics occurring in this change in its magnetic field. So, and we'll talk about the solar activity and the solar cycle based on this. So that's all a product of the differential rotation. Okay, so coming up to this idea here. So when we talk about solar activity, which is big, big science, and of course, this is why we like to keep track of the sun and monitor the sun, it refers to the magnetic field activity of the sun and its effects, which could really be very, very pesky when it comes to our electronics, especially our satellites. Now, the heliosphere is something that's referred to a lot in the solar system and with respect to the sun. This is the surrounding shroud of area or this volume or region of space that's the magnetic influence of the sun. And we have a lot of the magnetic influence of the sun, but lucky for us on Earth, we're shielded by the Earth's magnetic field. Okay, so we're able to protect ourselves from all these high charged particles traveling towards us from the sun. And we'll see that one of the dangers of space travel and exploring other planets like Mars is the lack of magnetic fields on other planets. And that can be very dangerous because that protects you from ionizing particles, which can lead to cancer and spikes. It will damage your cells, etc. So anyways, the sun has a huge magnetic field influence up to 1 AU and beyond. And it's filled with charged particles. And these charged particles are carried by something called the solar wind. The solar wind is just this stream of charged particles that are released from the sun's atmosphere. Okay. And then, as we noted before, the different rotation rates inside the sun make a change in the magnetic poles every 11 years. Now, that is really just a very, very loose approximation, because sometimes we'll be expecting it in 11 years and it hasn't happened. We'll wait another year, we'll wait another year. So a better range of figures is 7 to 15 years. Okay. And so it's really, we do see cyclic patterns in the North Pole changing to the South Pole and vice versa in the sun. So we could fine tune, we're still trying to fine tune the numbers, but it's very hard to predict again. So this is called the solar cycle. And right now we're actually at a solar minimum. And the solar minimum we'll see coincides with a low production of sunspot activity. If you virtually don't have any spots in the sun, but we do expect a maximum around 2023 and 2025, and we'll see more sunspots during that maximum. Okay, that's when it's about to turn into the South Pole's about to turn into the North Pole and vice versa. We'll also see a lot more flares and a lot more injections of ionizing particles and their effects on Earth, like the geomagnetic storms and auroras we'll talk about. Okay, so looking at some of these effects, the effects are the change of polarity, increase in sunspot appearance, increases in solar prominences, flares, and coronal mass ejections, CMEs. increased space weather activity. So that's another term that we use. So when we use the term space weather, what do we mean by that? We mean the charged particles carried by the solar wind that are from the upper atmosphere of the sun. So here's a better image for you. And I am just going to go back and give you a quick visual. There we go. So if we look at today's space weather, which deals with the sun activity, you can see that we are in a solar minimum. So if you look at the sun today, here we are. There's no spots. There's no projections of emitted flares or ejections of ionized particles. Okay. So we've had 2 spotless days in a row. Okay. And then we could check tomorrow and see if there's any more. So this website gives you alerts as well, and then tells you if there's any sunspot activity, any other activity, projections of charged particles that are emitted from the atmosphere of the sun, from the surface of the sun, which can influence electronics and satellites and produce auroras here on Earth. So here's one site that does a lot of information on the current state of the sun. And there's also the sun today, and it has space weather as well. Okay, and I'll tell you if there's any storms currently going on and projected maximum spikes coming up. So some good outside references. I always like looking at the space weather website to see if we have spots today or not. Okay, so this kind of gives you a good impression of what's going on here. Okay, so here's all the layers of the sun we were talking about. Okay, here's the photosphere, and here's where the photons leave, and here's the solar wind, and here's the Earth. So the Earth has this magnetic shield around it. So a lot of these charged particles just travel around. They go this way. Actually, I'm going to clear that. Okay, so they travel around this way. Whoa, I did it again. So it travels this way around the Earth. And then onto the outer planets, because we'll see that the solar wind is carried, like I said, 100 AU. So it goes all the way, goes to Jupiter, goes to Saturn, and we have these effects on those other planets as well. So the solar wind goes far out. Okay. And Voyager has basically gotten to the end of the sun's influence out there. So Voyager is right where the end of the sun's influence is, and this varies. So this is, the solar wind is just all those charged particles carried. So it goes around all these. And what happens is, if these are charged particles, here's the magnetic field of the Earth, and they just travel around there. Some of them are able to get into the polar regions by the way the geometry works, the magnetic field structure of the Earth. There are some areas where it could, the charged particles get funneled in to the polar regions. And when we have a lot of solar activity, increases in sunspots and ejections of charged particles, we actually see more what we call cosmic rays, and higher incidences of cancer have been linked to increased solar activity when you have these charged particles. Now, if you're in an airplane and flying an airplane, this is very dangerous because you're exposed in the upper atmosphere. There's more charged particles. It's just as the particles get towards the surface, you know, they kind of scatter mostly in the upper atmosphere or get absorbed, re-emitted, absorbed, re-emitted. But when they get towards the surface, it's not as dangerous as in the upper atmosphere. Planes, if you're flying an airplane, you tend to get higher doses of cosmic radiation that way. So if we have especially large eruptions from the sun, you'll get a lot more of those doses. Okay. Excuse me for 1 second. Here it goes. Okay. So lots of effects there. So this tells you, this gives you an image of the corona. Here's trapped gases. This is this is a coronal mass ejection. It's huge. Prominences are smaller loops that we'll see. And here's a sunspot. Okay, so this gives you an idea of how it works. So the heliosphere is what's containing all the solar wind. So moving to the next slide. All right. All right, here we go. Here's the sunspots. Okay. This is what, if we were looking at space weather today and we saw sunspots, we'd see something like this. And so these are cooler regions, that's why they're dark. And so here's a temperature range of 4,000 to 5,500 Kelvin. I see that range kind of all over the place online, so just be careful on what you're looking at. And they appear on the surface due to the increased magnetic field activity. Okay, so as it's changing its polarity north to south pole, we're producing these sunspots. And they typically start in the polar regions and migrate down. Okay, and they occur, a lot of times they occur in pairs. Okay, and we'll see loops where loops of material that passes between them connects one might be a southern polarity, one might be a northern polarity, and this comes up from just tangled magnetic field lines. You know, magnetic field lines are lines where the charged particles are making the flow of electric charges. So it's sort of hard to describe without going into detail, but these come from tangled magnetic fields. So just think of all these little strings or elastic bands inside the sun getting tangled up. And this is what's connected here. These are like parts of the magnetic field lines poking up through the surface of the sun. So what we typically see, we'll see plasmas connecting two spots. And I have to go on to the next page. And this will show you a good scale on size here. So, you know, typically a lot of these spots are Earth-sized, but every once in a while you get huge spots that are the size of Jupiter. And we could have them last 1 to 100 days. Groups can typically last 50 days. So maximum number of activity, again, in this solar maximum. When we hit our peak at 11 years, we'll see a lot. As we're getting closer to the flipping, we'll see a lot more of these sunspots. Now, what's really interesting, and this came up, and I just read this in the news too, because the dimming of Betelgeuse, the star, it's a red giant star, and we could do a nice problem if it's, you could look at the red color of light, the wavelength it gives off, about 700 nanometers or more, and then you could find its surface temperature, which is about 3,800 Kelvin. I'll say 3,000 to 4,000 Kelvin, just a rough estimate. So anyways, what we've noticed about Betelgeuse is it started to dim and get dimmer in the night sky. And everybody was like wondering if it's going to explode, the star in our sky. Betelgeuse is a star in the Orion constellation, by the way. But everyone was wondering whether it was going to explode this winter, what was going on. It was going to go supernova, whether there's a dust cloud in front of it that was shrouding our view of this star. However, the most recent data is showing that Betelgeuse might have just increased spot activity. It's a star that produces spots just like the sun, and it had a lot of spots on it. So of course these are cooler, darker regions, so it would dim the actual brightness of the star. So this is really interesting stuff that was coming up. So we're really looking at spot activity on other stars. I can't call them sunspots because other stars are not our sun. Okay, so anyways, here's our cycles and our forecast. So we can see, here's our July 2020 2025 prediction, our spike. We're on solar cycle 25. We've been tracking since the 1600s. So I posted that question on the discussion board, this link between temperature and sunspot activity. There is a link, but you know, the temperature rises in our current years are nothing compared to the temperature changes and fluxes based on sunspot activity. But there are periods of cooling and heating that are associated with sunspot activity. We had this cold time, and that was linked to this minimum of sunspot, of solar activity here. Okay. So here we are making our way into, we're just starting cycle 25. So you can mark that in your history books, in your astronomy textbooks, if you're keeping them. This is the start of cycle 25 when I took this astronomy class. So it should be interesting. And, you know, hopefully, you know, we'll see our first sunspot soon, you know, or significant sunspots occurring. But around 2025, we should see some peaks. Okay. So here we have the Solar Dynamics Observatory launched by NASA has just given us such a wealth of information. There's so many great images. And I posted a video of 10 years of images or video taken from the SDO where 1 day is equal to 1 second. And it just produced a lot. So this is, you have certain filters. We're filtering out the light. We're seeing, here we're looking at UV light, looking at the sun in UV light, which gives us different information. And we could see these loops, these high energy loops really well. These are called prominent, these are coronal loops. And a lot of these loops are prominences. They connect sunspots together. So you could see these are magnetic field lines. So another way of thinking about magnetic field that just came to mind, and I should have one here. If you've ever taken iron filings in a magnet, you'll see the pattern of the iron filings around the magnet. And those are it travels along magnetic field lines. So these are invisible lines, like elastic bands connected to the sun's magnetism, in which these gases travel and are trapped. Okay, and these are reconfiguring, they're twisting, stretching, and reconfiguring. So very, very active sun. Okay, here's a good way of looking at another solar prominence. So here we have the size of the Earth right here, and look at this solar prominence right here. So here we have this loop of gases that are trapped right here. Okay, so we have this loop of trapped gases, and these are connecting sunspots. And a flare is just a localized energy released when these loops are twisting around and changing. It gives off a little flare in the process. Okay, so they're released jets of energy. And then we come out here and we have the big stuff. So flare versus coronal mass ejection, CME is huge. So CME is like a huge release of energy. So, you know, here we have this prominence or these lines, and they just snap and they fling all these charged particles towards us. And that's what we call a CME. So that's a big picture of one right here. And it reaches Earth. If it's oriented in the correct way, like, you know, maybe a CME is going out in a different direction, not towards Earth. That's great. So we're constantly looking for monitoring incidents of coronal mass ejections. If we see these loops and we see them about to snap, and we have a lot of solar observatories watching the sun for that, because we have to turn our satellites. If we see it snaps and flings ionizing radiation in a different direction than the Earth, we're safe. But if we see it snaps and flings all this ionizing radiation towards Earth, guess what? We have to orient our satellites, our sensitive electronics in space, away from them, because what would happen is these charged particles traveling through the solar wind will hit the electrical components and then give this increase in current in the components, and then just like fry the electronics of our satellites. So, you know, satellites are not very cheap, right? We're talking millions and millions of dollars. So it could easily destroy satellites, and it has. There's been incidences of that in the past. I think in the 90s, we've had a lot of satellites destroyed. There was a big solar storm in 1989 that actually created a power loss in Quebec. All the charged particles got into the power lines, and we had power outages based just from the charged particles carried from a CME. Okay, so they reach Earth and they create what we call geomagnetic storms. This is the fun stuff. So geomagnetic storm, just a disturbance of Earth's magnetic field connected with solar activity. We get charged particles carried by the solar wind and they interact with the magnetic field. And this results in electrical disturbances and aurora activity at the north and south poles. So we have auroras, which are displays of light. And what happens with these displays of light, we get this light. So if we take the Earth, and I'll get a picture of just a little model of the Earth again. So we take the Earth and we take the polar regions. So the charged particles funnel in the North Pole, and they funnel in the South Pole, and we get the interactions of the charged particles with the atoms in the atmosphere create your different types of lights. So the different colors represent different atomic interactions. The blue that you see is from the charged particles interacting with nitrogen. Red is the oxygen molecule interactions, etc. So to make an aurora, all you need is a magnetic field, some atmosphere, plus some charged particles, and then you can make your aurora. So we also have them in other planets as well. So Jupiter has auroras, Saturn has auroras, etc. And there's two types during solar storms or solar activity. In other words, the aurora borealis is also known as the northern lights. And these occur around the north polar regions, but sometimes you could see them all the way down to California. If we have incredible solar activity, we could see it across the rest of the states. And there's been incidences of that in the past. The aurora australis is the southern lights, and this is at the geographic South Pole and the surrounding regions. Okay. And those are really, I'll post a good clip that we have on the auroras. But I'm looking for one more site here. Oh yeah, so here's the and the sun today has some really good pictures on the auroras. Okay, I know that places like Iceland actually have aurora tours, you know, but the idea is right now we're not supposed to see very much because we're at a solar minimum. So this really gives you a good view of how this works. So here we have the charged particles coming from the sun. Here's a good representation of the Earth's magnetic field. It's it goes around on the sides, but it funnels inward towards the polar regions. So as these charged particles come towards the polar regions of the Earth, get funneled in, they hit these molecules in our atmosphere that get excited and they give off light as they calm down. Okay, so it's really some fun science, and the product is amazing. I know they've taken a lot of photos from the International Space Station on the auroras, and those are some amazing photos. So it's interesting to look at them from the top. So all you're seeing right here is the interaction of the sun's charged particles with the Earth's atmosphere. Okay. So lots of photos out there. I think you've got libraries and libraries of photos. Okay, and now some current missions on the sun too. You could go to the website, NASA's website, and you have a lot of the missions that we have here. So here's the Decade of the Sun mission from SDO. The Parker Solar Probe is the newest, and solar observatory. Okay. So the Parker Solar Probe, I remember when they were proposing it and then they finally launched it. This is from 2018. And all these solar orbiters and observatories are really important. Well, like the idea is to monitor the sun 24/7 and try to get a big view of it, because if we see a spot on the other side of the sun that's appearing, there might be some connection with a solar storm coming, geomagnetic storm coming. And again, the danger is frying our electronics, especially our sensitive satellites out in space. Okay, so I'm going to stop this share, and I'll take any questions. If anybody have any questions they have for now?